Hello and welcome to Effortless Mastery. Today we'll be learning about glycogen metabolism, though we'll be dwelling on glycogenesis. Now, from the name, anytime we mention metabolism is always two-faced, build up and breakdown. So you see the build up, that is, in this case, glycogenesis, generation of glycogen, the formation of glycogen from glucose. So that is build up. So we call it glycogenesis. On the other hand, we have glycogenolysis. I am breaking down something, glycogenolysis, and that is the breakdown of glycogen to return to form glucose. Now, why are we bringing up this? It's very important that, like we mentioned earlier in our series, that the end product of digestion of carbohydrates is glucose. Now, glucose, after a meal, there is enough glucose in blood. Excess glucose is stored majorly in two locations, the liver and skeletal muscles, and are stored as glycogen. And then during starvation or during fasting state, you realize that those people that were stored, this glycogen that was stored will now be broken down to fill the body with glucose. This is a mechanism by which the body ensures that at all times, to some extent, there is supply of glucose. So after a meal, the glucose that is formed is supplied to the body, excess is stored. During fasting state, during starvation, that excess is broken down to still give glucose energy so that it could be used for energy. Now, for today's class, we will really dwell on one phase of this metabolism, which is glycogenesis. Glycogenesis. So stay true with us and let us enjoy how this happens. Glycogenesis. Now, from the word glyco, here is glycogen, whereas genesis means formation. So glycogenesis in simple terms is the formation of glycogen from glucose. The formation of glycogen from glucose. Now, where does it occur? It occurs, like I said, it occurs primarily in the liver and in the skeletal muscle. So first and foremost, this thing we call glycogenesis is actually the formation of glycogen from glucose. Now, where does it occur? Primarily the liver and the skeletal muscle. It is very important you know the locations where it occurs, the liver and the skeletal muscle. Now, this generation of glycogen from glucose is the main enzyme or the key enzyme that is very important in this pathway. Is called glycogen synthesis. Now, from the name synthesis, of course, when we learned, or if you've been exposed to classes of enzymes, you'll be taught of a particular class of enzymes we call synthase. Now, this oddly, so one of them, ligases, are people that can form or generate something. So synthase is one of them. That is where it falls under. So from the name synthase, glycogen synthase, an enzyme important in the synthesis of glycogen. So please, it is the key enzyme in this pathway. So the key enzyme in this pathway is what? Glycogen synthase. Now, the key things to note about this enzyme, though we'll talk about regulation of this enzyme as a separate video, but the key thing I would love you to know about this enzyme is that, number one, this enzyme is active in dephosphorylated state. That means it is only active when it is without phosphate. Rather, on the other hand, so this guy is active in dephosphorylated state, whereas it is inactive in phosphorylated state. So what are we saying this to say? I'm saying this to say that the only time glycogen synthase is active is when he is without phosphate. This will be important when we talk about the regulation, because you get to hear that what is responsible for its activation is actually a protein or an enzyme we call protein phosphatase that cleaves out phosphate. So you now realize that is why he is activated. So you watch our video on regulation, I'll dwell more on how they are regulated. But for now, the key enzyme is glycogen synthesis. Where does it occur? In the liver and skeletal muscle. What is glycogenesis itself? Formation of glycogen from glucose. Now, the next thing that is important is, how does this pathway occur? How is this achieved in the human body? How does this pathway occur? Now, glycogenesis begins in the liver. So if this is the liver I'm looking at, it is very simple. The steps of this process is very direct and simple. Now, it begins with glucose being converted to glucose 6-phosphate. And if you observe, glucose here is without a phosphate, but glucose 6-phosphate, from the name, it has a phosphate. And like we mentioned in our glycolysis video, now, for me to have an addition of phosphates, there is a source for the phosphate. And in this case, the source of phosphate is ATP. The source of phosphate is ATP. So what happens? ATP is hydrolyzed to give ADP. So ATP, triphosphate, 3-phosphate, is changing to 2. Why? He has transferred one of it to this guy. And enzymes that transfer phosphate from one person to the substrate is usually called kinases. So please remember that kinases are enzymes that do what? Transfer phosphate. So when I look at this, glucose is changing to glucose 6. The name of this enzyme is kinase, and it is specifically exokinase. But I'd love to mention something that's very important. Now, exokinase is seen in different cells of the body, but there's a particular specialized type of exokinase. Exokinase here is showing generally I should be able to act on different people. Exo, 6 carbon, transfers phosphate to a 6 carbon sugar. Now, but when we are more specific, the kind of exokinase or kinase we have in the liver is called glycokinase. So from the name glycokinase, this kinase is specific for glucose. It is found way in the liver. And what it does is that instead of giving from glucose to glucose 6, it will go from glucose to glucose 1-phosphate. I'll mention the importance of this in a very short while. But for now, this exokinase, glucose to glucose 6-phosphate, is going to be happening more in skeletal muscle. But in liver, we're looking at a case where it is actually glucokinase, which will put it in 1. But let's go on. Now, from here, glucose 6 is converted to glucose 1-phosphate. And the name of the enzyme responsible for this, for catalyzing this step, please, we have cofactors. I had mentioned this earlier when we dealt with this, that cofactors, let me use magnesium only, that the cofactor for this reaction that involves hydrolysis of ATP and transfer of phosphate is usually magnesium. Yes. So right here, I'm moving from glucose 6 to glucose 1. Now, if you observe from an idea of basic organic chemistry, isomerism, this is actually an isomerism reaction where there is just a change in position of a substituent, which in this case is phosphate. So phosphate is changing position from number 6 to number what? 1. So 6 to 1. And the name of the enzyme is called phosphoglucomutase. I'll tell you why the enzyme is named this way. Phosphoglucomutase. So if you look at the enzyme phosphoglucomutase, now phosphoglucose, that's I'm dealing with a glucose that has a phosphate. Mutase from the word is derived from the word mutation. You know what mutation is? Mutation is a permanent alteration. When I'm changing something, alteration from normal, the permanent alteration in the normal sequencing of a particular gene, it happens more. Mutation is a different topic entirely when we learn genetics. But right here, what I want you to see is that the normal idea is that whenever glucose is you're using exokinase, the addition of phosphate is to number 6. For me to change from the original place it should be to another place, the enzyme is called a mutase because it brings about something that would look or depict mutation. I believe you're following me. So please, that's why it is called what? A mutase. So it's to convert from 6 to 1. So you just change in position of the phosphate. So that covers step 1 and step 2. Now in step 3 of this pathway, please, you observe I showed it's reversible. That's because it could go both sides. I could still want to change from 1 to 6. We'll show that when we are dealing with glycogenolysis. But let's go on. From here, glucose 6 reacts with UTP. So now you see UTP. UTP is called uridine triphosphate. So uridine. So now UTP right here has 3 phosphates. Glucose, 1 phosphate, has how many? 1. So what happens here is that UTP will donate 1 phosphate to this guy. It will break the bond. So let me draw quickly a structure that looks like this is the glucose structure. So we have carbon 6. So carbon 1, carbon 2, 3, 4, 5, and 6. So follow through with me. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Now, what happens is that at carbon 1, this is where I had my phosphate initially attached. What this guy does is that it will split, it will hydrolyze to give me UDP and PI, inorganic phosphates. The inorganic phosphate plus this other phosphate, it will break this bond. 2 of them will now form something we call pyrophosphate, PPI. And then the UDP will replace. So the UDP will come in here instead. And what I'm forming will be called UDP glucose. I had to use black to make you see how distinct it is. Please look up. Now, so I'm changing from glucose 1 phosphate to UDP glucose. How is this achieved? Glucose 1 has how many phosphates? Only 1 of them in it. Now, whereas UTP is having 3. So it's as if I'm bringing 1 plus 3. Look at what to now form at the end of the day. PPI, 2. UDP, 2. So you realize that I'm still having 4 phosphates at the end of the day. How is this achieved? UTP is hydrolyzed to give UDP plus inorganic phosphates. The inorganic phosphates, when brought into this compound, causes a split, so that the phosphate that was already present in the compound joins him and comes out as pyrophosphate, PPI. And then what replaces that phosphate is the UDP we have here. And that's why what I form after this is called UDP glucose. And the enzyme that catalyzes this step, the way the enzyme is named, it's named as if I was reversing the step. And the enzyme is called UDP glucose pyrophosphorylase. Pyrophosphorylase. UDP glucose pyrophosphorylase. So please, UDP glucose pyrophosphorylase. So please, let's get this very clear. Now, I'm done taking food. End product of digestion, glucose. Food is carried away, liver, by hepatic portal vein, can be circulated to different parts of the body, one of which is skeletal muscles. Now, at the liver and skeletal muscle, glucose is not just going there to be used for energy. Now, of course, when we keep forming our normal glucose to glucose 6, it should enter glycolytic pathway. But as I keep using and forming energy, it will get to a threshold that the body knows there is no need to form energy again. Rather, let me stop. Now, it is not wise that you consume everything that comes in. That's why we learn of in monetary deals or in business, the business world, we learn about having to save, having to invest. All those are means to ensure you don't waste resources. So when resources come in this case glucose, they will keep changing, forming glycolysis for energy. But as time goes on, they know I have to stop. So when I form glucose 6, instead of going on to enter glycolytic pathway, the glucose 6 is changed to glucose 1, an enzyme called a mutase. And then this glucose 1 is he reacts to this glucose 1, we transfer UDP glucose. So what we are doing is that the UDP glucose is targeting carbon 1. the same place I had phosphates. So what do we do? UTP will be hydrolyzed to form UDP plus what? Inorganic phosphate. That UDP goes to replace my phosphate so that I can now have UDP glucose. But that phosphate that comes out joins with the other inorganic phosphate to come out as pyrophosphates called PPI. And the enzyme is called UDP glucose pyrophosphorylase. I'll talk about phosphorylase later when we deal with glycogenolysis. Okay, so that's that. So from here, please, UDP glucose is the donor of glucose. So he's someone that donates glucose to a glycogen primer to form glycogen. Now I'll take a bit of a pause to just mention a little bit about glycogen that is going to help our knowledge of what we are doing today. A little bit about glycogen that is going to help the knowledge of what we are doing today. Now, from basic biochemistry, we are taught that glycogen is a polymer of glucose. So it is a polysaccharide. So it's specifically an homopolysaccharide. So it is a polymer of glucose. But the key thing that distinguishes glycogen from starch is that glycogen has both single, that is straight and branch chain. Whereas when I look at a starch molecule, all it has is straight chain. Usually the structure of starch would be this way. So if this way, my glucose molecules, if this way my glucose molecule, this is what I'll be having. They will keep binding like this. And like you see, this is a straight chain structure. And if I want to be more specific, remember, I labeled this carbon 1. This is carbon 2. This is 3. This is 4. This is 5. This is 6. Same thing 1, 2, 3, 4, 5, and 6. Don't get confused. If you observe, I've not clearly shown every single thing about a glucose molecule. Of course, it's not necessary to what I want to explain to you. Like showing that there should be an OH down here, OH down here. I'm skipping that because there's something I want to highlight here. Now, from here, this will still be 1, 2, 3, 4. You realize for every straight chain structure, the bond is always between carbon 1 of one glucose molecule with carbon 4 of the next glucose molecule. And these kind of bonds are called alpha 1, 4 glycosidic bond. Alpha 1, 4 glycosidic bond. These are the only kinds of bonds we will see in starch. Whereas when I go to glycogen, the nice thing about glycogen is that while glycogen has these straight chain structures, which is alpha 1, 4 glycosidic bond, at the same time, there is a bond between 1 and 6. So let me draw another guy here. So I will have a bond between, so of course this should still be my 1, 2 and the likes. Now, if you see in this, between this guy and this is number 1, this is number 4. So this is an alpha 1, 4 glycosidic bond. Whereas when I come in, any place of branching is represented as alpha 1, 6 glycosidic bond. What do I want you to take away from what I'm showing you right now is that whenever I'm dealing with starch, the bond or the type of structure or the type of arrangement of glucose in starch is only in straight chains, having only one kind of bond, alpha 1, 4 glycosidic bond, starch, storage form of glucose in plants. But when I come to the storage form of glucose in animal called glycogen, I have these straight chains. Of course, it's not this short. The straight chains, which is alpha 1, 4 glycosidic bond. And I still have another type of chain, which is between 1 and 6. And that brings in branching. So glycogen, please take note, is made up of both straight chain and branch chain. Whereas starch is made up of only what? Straight chain. Don't forget that. Glycogen is made up of straight chain and branch chain. And that straight chain is alpha 1, 4. Branch chain is alpha 1, 6. Whereas starch is made up of only straight, which is alpha 1, 4. Now let's go on. I mentioned that UDP glucose here is a donor of glucose. So the function of UDP glucose is just to donate glucose to something we call glycogen primer. Or another name is that we call him, aside from glycogen primer, we can call him glycogenin. Now, it is very important I mention this. Remember I told you at the start of the class that the key enzyme in glycogenesis is called glycogen synthesis. So if that is true, the step here we want to go into is the main things that brought us here, which is the steps that can be catalyzed by this enzyme called glycogen synthesis. But you can note this in your book, that glycogen synthesis cannot just form this bond between one glucose with another to form glycogen. It cannot do it. So glycogen synthesis cannot form alpha 1,4 glycosidic bond without you already having 4 glucose residues. Listen very carefully. Glycogen synthesis can only add glucose to a template that already had up to 4 glucose residues. 4 or more. So I cannot add glucose to anything lower than 4. Hence the need for something called glycogen primer. Another name is what? Glycogenin. Now what does glycogenin or glycogen primer do? Glycogen primer, I'll write it down shortly. I could just say he's this ball here. It's just like a primer that activates the pathway. What does it do? Oh, I am here. The first UDP glucose will come in. Give him glucose. He collects 1. If glycogen synthesis come, can he act? No. Why? This thing has only 1 glucose. He calms down. Next thing, the same glycogenin. Some books talk about it as an autocatalytic effect. So this glycogenin here is acting like the substrate glucose will be transferred to. At the same time, glycogenin is acting as if it's an enzyme. So I don't need any enzyme to catalyze this step I'm talking about. It is still glycogenin doing what it wants to do. So once I have UDP glucose formed, glycogenin, also called glycogen primer, comes in, gets 1 glucose. I will show you how the step happens shortly. It gets 1 glucose from here, forms 1, gets again, and then he keeps forming. He gets again and forms another. He gets again, forms another. He gets again and forms another. Once I have up to 4, this is the only time glycogen synthesis can be called into action. I believe you are following me. So it is very simple. From UDP glucose, what's the function of UDP glucose? He wants to donate glucose and then, of course, release UDP. Donate glucose to the compound, release UDP. But like I said, the enzyme that should catalyze this step should have been glycogen synthesis. But glycogen synthesis cannot act without having a template that has 4 glucose molecules already. So what do we have right here? I'll have my that is UDP glucose, reacting with glycogenin, also called what? Glycogen primer. So when they react together, what happens is that the UDP glucose will donate glucose and come out as UDP. And then what I'll be having will be a glycogenin that has collected glucose. And I'll keep getting glucose, and then you realize what this will form ultimately. From what you saw, I'm showing you straight chains. So what it will form will be something, a glycogen molecule that has just only 1,4 glycosidic bonds. So I'd like you to follow through with what I said. From here, I donate to glycogenin to make sure it's up to 4. The enzyme there is like glycogenin. But ultimately, when we look at the books, what the books do is that after 4, the person that catalyzes any further addition to now keep elongating from 4 to as long as possible is the key enzyme of glycogenesis. And that enzyme is called what? Yes, you got it. Glycogen synthesis. That is the enzyme, glycogen synthesis. So after I've had the first 4 being added by glycogenin from UDP glucose, I now any further elongation is by an enzyme called glycogen synthesis. And remember, this enzyme is only active in the enzyme is only active in dephosphorylated state. So that brings us to only alpha 1. But like we said, when we deal with glycogen, glycogen does not only have straight chains. Glycogen has straight chains and what? Branch chains. So what is the source of how do I now get the branching? This is where we bring in another enzyme. And this other enzyme is called branching enzyme. So what happens is that elongation will happen. First, glycogenin will give us a template. Go in, pick first glucose, pick second, pick third, pick up to 4. After you pick up to 4, glycogen synthesis keeps elongating. And what we are told and what happens in the human body is that by the time we have up to 11, 12, as far as you've gotten to 11, another enzyme is called in, and this enzyme is called branching enzyme. What is the role of this enzyme? Very simple. It just comes in. Let's say this way, my guys. I had my black guy. I have had from 1 to around 11. You keep going. What does branching enzyme do? It will just come in, cut a part of that is, after I have had elongation, I keep having straight, it will cut. And when it cuts, it brings it up and binds with another person. Remember, as far as they are doing straight chain, which bond are they forming? Alpha 1, 4. Branching enzyme brings in a second bond called alpha 1, 6. So from here, this is what I mean happens. From here, this enzyme is called branching enzyme. And what does the enzyme do? The enzyme ensures that we don't just have alpha 1, 4. We also add plus alpha 1, 6. And once you have alpha 1, 4 and alpha 1, 6, this structure you have here is called glycogen. So glycogen is only formed after branching enzyme has done its work. And funny thing is that branching enzymes work. This thing though is not like it's gonna stop here. The stuff is glycogen synthesis will keep elongating. You keep elongating. As you keep elongating, branching will keep cutting it to form the bond. Remember I said that other bond is 1, 6. You keep elongating to form the bond. And that brings us to the formation of glycogen, which is what we were aiming at. Formation of glycogen, glycogenesis. So now what have we learned? What is the summary of what we've done today in glycogen synthesis? We started by establishing that glycogenesis or glycogen synthesis is actually the formation of glycogen from glucose. But one thing is important. Glycogen, unlike starch, has both straight chain and branch chain. So there is branching, both straight glucose units, from a straight chain of glucose units and then branch chain of glucose units. So because of that, what we'll need 2 enzymes. Of course, the key one is glycogen synthesis, but we'll be needing another enzyme called branching enzyme. But how is this achieved in the human body? Very simple, step by step. The glucose I take in, after excess glycolysis, I no more need energy, I want to store in 2 primary locations, the liver and the skeletal muscle. At those locations, glucose is converted to glucose 6 by an enzyme called exokinase. Now, glucose 6 phosphate is now changed to glucose 1 phosphate. And then the enzyme there is a mutase. So now, when I want to move from 1, what happens is that UTP comes in to donate UDP to glucose and form UDP glucose. But by doing that, he has lost 1 phosphate. The UDP replaces the phosphate that was here, so that I can now have PPI come out, forming UDP glucose. Now, very simply from here, glycogenin. Now, this UDP glucose is a donor of glucose. Now, but the way it donates glucose, who it donates glucose to is glycogenin. Why is this so? Glycogen synthesis cannot act. I have repeated this countless times. I want you to have it with you. Glycogen synthesis cannot act. It cannot form this bond without having a template that had up to 4 already. So the function of glycogenin is to give him that template. So come in, pick the first glucose, pick the second one, pick the third, pick the fourth. After he has up to 4, glycogen synthesis is now called into action. The essence of glycogen synthesis is to transfer glucose to that chain we had already. But the aim is that I'm forming only alpha 1 for glycosidic bond, and that is just elongation of the chain. Now, with continued elongation, when we get to about an elongation or a chain that has up to 11 glucose residues, another enzyme is activated called branching enzyme. The enzyme here is aimed at ensuring branching is brought in. So what happens here? I come in here, I break. Let's say I had from G1 to G11. That's the G's here are glucose moieties or glucose molecules. I cut it, and we are told it could cut like up to 6. I cut the 6, knowing that glycogen synthesis will come back and elongate. So I cut and then carry it back to go and bind somewhere. Now the new bond I'm forming is now alpha 1,6. So the structure that has alpha 1,4 and alpha 1,6 bonds of glucose is called a glycogen. That structure is called a glycogen. So what is the takeaway? What is the salient point to note from here? What are the takeaways to note from today's class? The things to note now, number one, you take note of the definition, you take note of the location of where does it occur, the site it occurs. You take note of the steps, the enzymes, and very keenly the key enzyme, which is glycogen synthase, and another key enzyme we call branching enzyme. So thank you very much for joining us today. I look to see you in our next class where we'll be talking a lot and dwelling on the breakdown of this glycogen that has been formed, a process called glycogenolysis.